this ASMR video. I hope you're all out here living life to its fullest potential each and every single day. Today we're back on the space vibe with a dash of physics as we touch on one of the most monumental breakthroughs of the modern scientific era, being none other than the theory of relativity by the man himself, Mr. Albert Einstein. The theory is responsible for a whole bunch of things in our day-to-day lives that we're probably unaware of. So, it's a huge part of history. It shapes a lot of modern-day physics, and we're going to be going over everything today. Before we begin, if you're into ASMR, interesting topics, and in general just expanding your knowledge, then you've come to the right place, because it's all we do, and we upload 2 to 3 times every single week. So if that's your thing, then be sure to subscribe and hit the bell icon to be notified every single time we upload a new video. Okay, with that being said, let's jump right into today's video. Einstein formulated 2 theories of relativity, special and general. Both deal with time and space, special relativity with motion and speed, general relativity with space-time and gravity. Einstein started with 2 axioms. First axiom: absolute motion cannot be proven. Absolute motion is the idea that a thing can be said to be moving with no frame of reference whatsoever. So for example, if you yourself were floating in a never-ending white space with no one and nothing else, no corners or distinctive factors, if you tried to move, you wouldn't be able to say with any certainty if you were moving or not. You would have no reference again, other than yourself. The only way that you know you'd be moving is if a second thing existed in your never-ending space from which you could reference if you were getting closer, further away, or moving parallel, etc. If a floor existed and your feet touched it, that would be a frame of reference, and you could say that you were moving across the floor. But that would not be absolute motion, because 2 frames of reference would exist, you and the floor, and one is moving relative to the other. A thing can only be said to be moving relative to something else. Currently, I'm sitting at my desk and a car is driving past outside. Is the car moving relative to me, or am I moving relative to the car? Well, since I'm sitting in a room, at a desk, a chair, a lamp, and I'm stationary, as I am, and the car is moving away from all of us at the same rate, it can be said that the car is moving relative to me, not the other way around. What if the car stops though? Then neither of us are moving, right? We're all stationary, but we're stationary relative to each other. We're both sitting on the Earth though, and the Earth is moving through space at 11 miles per second. The Earth can be said to be moving relative to the Sun. So even though both myself and the car are not moving relative to each other, we're both sitting on the Earth moving around the Sun. So we can be said to be moving at the same rate through space. Einstein's first axiom shows all motion is relative. Second axiom: the speed of light is constant. The expanded version: the speed of light is constant in a vacuum and is the same for all observers in the universe, regardless of the rate of motion of the observer or the source. To say the speed of light is constant sounds unremarkable at first. It just states that light always travels at the same speed. Once we start considering what it means though, some incredible consequences emerge. The speed of light is 299,792,458 meters per second. Wow. Just for ease, we'll refer to it as 300,000 kilometers per second. Oh, and guys, apologies for the wind outside. Again, it's a very windy day here at my house. So, anyway, back to the video. This is an unfathomably fast speed. Just to put it into speed of light, you would circle the Earth just over 7 times in a single second. You could reach the Moon in 1.3 seconds, Mars in 3 minutes, and the Sun in 8.20 minutes. The speed of light in a vacuum does not accelerate or decelerate. It always travels at a constant speed, known as c, otherwise known as the cosmic speed limit. The speed of light must remain constant for all observers. To say the speed of light is the same for all observers, regardless of how fast the observer is travelling, is to say if you were standing still, light would be travelling away from you at 300,000 kilometers per second. Okay. It's also to say that if you were travelling at 100 miles per hour, light would still be travelling away from you at 300,000 kilometers per second. It's also to say that if you were travelling at 290,000 kilometers per second, light would still be travelling away from you at 300,000 kilometers per second. But how could this be? If you were travelling within 95% of the speed of light, how could it still be catering away from you at its full speed? If you were chasing a particle of light and you were travelling at 290,000 kilometers per second, would it not just be the net extra 10,000 kilometers per second in front of you? Well, apparently not. It would still be travelling away from you at 300,000 kilometers per second. How is this possible? Which brings us on to our next section, which is speed. We get the measure for speed by dividing distance by time. You take the distance you've travelled and divide it by the time it took you to get there. If you travelled 120 miles and it took you 2 hours, you travelled at 60 miles per hour. We can perform a simple thought experiment to demonstrate speed as a concept and the constants of the speed of light. So there's actually a small video or a GIF as such that I'm going to add onto the screen right now, and there'll be a few more coming in the near future just to kind of explain this a little bit better. So imagine 2 mirrors directly facing each other, one above and one below. Now imagine one particle of light travels from one mirror to the other. We'll call this particle photon. Mirrors reflect light, so the photon would just bounce back and forth between them. Now let's put some measurements on this. The actual units of measurement don't matter. Let's just say there's a distance of 1 meter between the mirrors. The photon travels 1 meter when it leaves one mirror and reaches the other. We also need to add the unit of time. Imagine a clock on top measuring the time it takes for the photon to travel 1 meter. Or just look at the image. Let's say it takes 1 tick of the clock for light to travel from one mirror to the other. So our beam travels 1 meter in the time of 1t. Simple stuff. Now remember, the speed of light is constant. It doesn't speed up or slow. It always travels at the same rate. If we leave our beam as it is the photon, it will, the photon will just bounce between the 2 mirrors forever, like it does in the GIF one. Now let's add some position for the mirrors. We'll define 3, A, B, and C. Imagine when the photon leaves the mirror, when it leaves the bottom mirror, the top mirror moves from point A to point B. Our beam of light leaves the bottom of point A and reaches the top mirror when it's moved to point B. Now the distance is clearly longer between bottom A and top B than it is from bottom A to top A. We said the distance between top and bottom is 1 meter and it takes a time of 1t. We can see the distance from bottom A to top B is 1.5 meters. So our beam of light has travelled a longer distance and therefore should have taken more time to get there, right? Again, a apparently not. This is where we must remember the speed of light is constant. It cannot take any more time to get there, even though the distance is longer. The time it takes must still be one tick, even though it travelled further in distance. Remember, speed equals distance slash time. We can flip it to distance equals speed x time, or time equals distance slash speed. The speed cannot change, so we must change something else, and because the speed must stay constant, time and distance have to change. Einstein discovered that, like motion, time is not an absolute concept. Time is malleable, and technically everyone has their own measure of it. Gravity affects how fast or how slow time moves, and technically speaking, because the gravity is slightly larger at your feet than it is at your head, because your feet are closer to the centre of the earth, time moves a little bit slower at your feet than it would do at your noggin, if that makes sense. The distance is so tiny though, it's less than negligible. This effect of stretching of time is called time dilation, and it's exactly what happens for the photon in our light clock. The speed of light must remain constant, even though it travels further. It cannot take any longer to get there. It must take one tick, so time stretches to compensate. This concept seems baffling at first comprehension, but it agrees with every experiment so far. Time moves slower because the faster a thing travels, the more time dilates, as in stretches, for it, according to Einstein's theory of special relativity. This means, hypothetically, the faster you travel, the slower you age, but humans cannot travel anywhere near fast enough for time dilation to have any significant effect at all. So, if that is special relativity, then what is general relativity? I'm glad you asked, because that's exactly what we're going to be looking at right now. So, essentially, it's a theory of gravity. The basic idea that instead of being an invisible force that attracts objects to one another, gravity is a curving or warping of space. The more massive an object, the more it warps the space around it. For example, the sun is massive enough to warp space across our solar system, a bit like a wave. The way a heavy ball resting on a rubber sheet warps the sheet. As a result, Earth and the planets move in curved paths, i.e. orbits, around it. This warping also affects measurements of time. We tend to think of time as ticking away at a steady rate, but just as gravity can stretch or warp space, it can also dilate time. If your friend climbs to the top of a mountain, you'll see his clock ticking faster compared to yours. Another friend at the bottom of the valley will have a slower ticking clock because of the difference in the strength of gravity at each place. Subsequent experiments prove that this indeed does happen. So, what kind of tests have been done to prove this? Well, over the last century, many experiments have confirmed the validity of both special and general relativity. In the first major test of general relativity, astronomers in 1919 measured the deflection of light from distant stars as the starlight passed by our sun, proving that gravity does in fact distort or curve space. In 1971, scientists tested both parts of Einstein's theory by placing precisely synchronized atomic clocks in airliners and flying them around the world. A check of the timepieces after the planes landed showed that the clocks aboard the airliners were running a tiny bit slower, less than 1/millionth of a second than the clocks on the ground. This disparity resulted from the speed of the planes, a special relativity effect, and their greater distance from the centre of the Earth's gravitational field. as in general relativity. In 2016, the discovery of gravitational waves, subtle ripples in the fabric of space-time, was another confirmation of general relativity. So, in what instances has this affected the world that we live in today? While the ideas behind relativity seem esoteric, the theory has had a huge impact on the modern world. Nuclear power plants and nuclear weapons, for example, would be impossible without the knowledge that matter can be transformed into energy. And our GPS satellite network needs to account for the subtle effect of both special and general relativity. If it didn't, they'd give results that were off by several miles. Cool. So, finally, let's talk about E equals mc squared just a little bit. E equals mc squared is the world's most famous equation, but what does it really mean? Energy equals mass times the speed of light squared. On the most basic level, the equation says that energy and mass, matter, are interchangeable. They are different forms of the same thing. Under the right conditions, energy can become mass and vice versa. We humans don't see them that way. How can a beam of light and a walnut, say, be different forms of the same thing? But nature does. So, why would you have to multiply the mass of that walnut by the speed of light to determine how much energy is bound up inside it? The reason is, whenever you convert part of a walnut or any other piece of matter to pure energy, the resulting energy is, by definition, moving at the speed of light. Pure energy is electromagnetic radiation, whether light or X-rays or whatever. The electromagnetic radiation travels at a constant speed of 300,000 kilometers per second. Why, then, do you have to square the speed of light? It has to do with the nature of energy. When something is moving 4 times as fast as something else, it doesn't have 4 times the energy, but rather 16 times the energy. In other words, that figure is squared, so the speed of light squared is the conversion factor that decides just how much energy lies within a walnut or any other chunk of matter. And because the speed of light squared is a huge number, I believe the number I'm looking at here is 90 billion kilometers per second squared. That's 90 with 9 zeros, by the way, so I think I'm right. The amount of energy bound up into even the smallest mass is truly mind-boggling. Here's an example. If you could turn every one of the atoms into a paperclip, every one of the atoms in a paperclip into pure energy, leaving no mass whatsoever, the paperclip would yield 18 kilotons of TNT. That's roughly the size of the bomb that destroyed Hiroshima in 1945. On Earth, however, there is no practical way to convert a paperclip or any other object entirely to energy. It would require temperatures and pressures greater than those at the core of the Sun. And on a side note, for those of you that don't know, those kind of temperatures cause nuclear fusion, which, again, I'm also probably going to do a video on because that is super interesting. And how one particle accelerator company on the planet, I believe it was called CERN, the company's called CERN, managed to just about achieve that, only for a few seconds, but it did manage to achieve nuclear fusion on Earth. It's one of the hardest things to do, and if we could harness that energy successfully, actually hold the energy, then it would fix all of the energy problems on Earth, because it's basically the power of nuclear. It's basically the same as nuclear power, but without the radiation, so without basically all of the side effects and the negatives that come with nuclear power. But anyway, like I said, we'll save that for another video. And with that brings an end to our video. I hope you found it insightful, relaxing, and learned a thing or two along the way. Clearly, this topic has so much depth and way more than we could go into today, and to be honest, probably way more than my little brain could even comprehend. My hat does go off to the scientists that discover and and study this stuff. Like, even after going over this with you now, a lot of it still doesn't quite add up to me. Like, how can time be physically distorted by mass and gravity? To me, surely time is a made-up value that humans have put on it, just for convenience in our own lives. So to think that it's actually a physical thing that's bound into the fabric of the universe, yeah, mind-boggling stuff. Also, I heard somewhere that if you're on a plane travelling at the speed of light, or near to the speed of light, and you walk down the aisle, you would actually be walking in slow motion. So I guess that kind of ties in with everything we spoke on today. But yeah, I heard that somewhere, so I thought I would drop it in there at the end here. But yeah, with that being said, this is the end of the video. If you did enjoy it, please feel free to give it a cheeky thumbs up. And if you really, really enjoyed it, you could even potentially, possibly consider subscribing. Who knows? But regardless, I appreciate you joining me today for some space-time ASMR. And I hope to catch you on the next one. Stay blessed, stay balanced.